Head movement can be gaze-driven to support our visual system. For example, when we direct our attention to look at a target. Or it can be independent of gaze as gestural expression, like when we use head movement to steer a ball into a hole while looking at a target. Both types are of utility to HCI, but differ in affordances. To facilitate their treatment as distinct modes of input, we collected data through a controlled experiment and developed a classifier with an F1 score of 0.89. We call it HeadBoost. In the following demo, we show how it is feasible and relevant to human-computer interaction with 3 applications. In application 1, we demonstrate HeadBoost can be used to ignore head gaze to avoid accidentally triggered interactions. Here the green dot shows where my eyes is looking, and the red dot shows where my head is pointing. In this task, I will use head gesture to swipe the cards to their correct species. Avians to the left, mammals to the right. Now I would like to look at the dog. So the next head movement is a head gaze and should not trigger a swipe. Now continue. Now I would like to look at all my avian cards. The next head movement is a head gaze and should not trigger a swipe. Now to finish. With HeadBoost, designers can leverage simple head gestures without worrying about Midas Touch caused by head gaze. Application 2 demonstrates that users can use head gestures to interact with contents in the current attended display and use head gaze to switch to a different display. Here in the current window, I want to use head gesture to swipe some avian cards. Now I want to switch display, so the next head movement is a head gaze and should not trigger a swipe, but to center the mammal display. Now I want to swipe some mammal cards. Now I want to switch window again and swipe a card. Change to the mammal window and swipe a card. HeadBoost enables multiple head-based systems to coexist without them accidentally triggering each other. Application 3 is an adaptation of the bimodal gaze pointing technique by Denmark and colleagues. Cursor is primarily controlled by gaze, but if the eye tracking accuracy is too poor, head gestures can be used to move the cursor into its desired location. Here, the cursor position is represented by the white dot. The green dot represents where I'm actually looking, and the red dot is my head. On the top, there's a list of animal cards, and when the cursor lands on one, its information is shown at the bottom. For example, now I want to look at the information about this dog on the right, but the cursor is too far offset. I need to perform a head gesture to refine its position. And now look at the text at the bottom. When I did that, the system detects a head gaze and switches back to gaze pointing. And one more time, if I want to look at the leftmost card, I perform a head gesture to refine the cursor position. Now look at the text at the bottom. The system detected a head gaze and switched back to gaze control of the cursor. We demonstrate that HeadBoost classification of head gaze and head gestures can be leveraged in the same interaction technique to switch interaction modes depending on the current needs. The classification of head gaze and head gesture enables seamless interaction using simple head movements.